Right, here's problem 3 in homework 11. We have a U-Heart contraption where we have this block right here at A and it's being lifted up. And this is like a really thin rod, so its mass doesn't matter. Otherwise, we'd have to be a little problems. We'd have to worry about, excuse me, oh boy. We'd have to worry about being rigid bodies, but I think we're okay. It's still dealing with particles. Anyway, it's released from the position shown where this is like 60 degrees and it strikes this cart that's about 1 kilogram. And it's on these little frictionless wheels and it goes up a slope and then it pauses, right? And some other dimensions like this beta is given as 30 degrees, this A is 0.6 meters and B is 1.6 meters. And the coefficient of restitution is 0.7. We want to find the distance up the slope from this point upward. So I said up from the curvature, that S is what we want to find. And we want to find the efficiency of the process. So I would say of the problems that we have to do here, this is probably the easiest of the 3, I think. And it's got a lot of work energy, or actually conservation of energy type of stuff. But we have to kind of like march through here. So let's see, did I write down any notes on this problem? I think I did. Okay. Yeah, so what I decided to do on mine was to break this up into 4 stages, right? So right here is going to be state 1. Right here is state 2, right? And that's just before impact. And state 3 is just before after impact. And state 4 is right there. So my first thing I need to do, I do a work energy thing. So I'll use KE1 plus PE1 is I don't want to leave out the work, plus U1 to 2 is equal to KE2 plus PE2. So my kinetic energy at the beginning is equal to 0. My potential energy at the beginning is going to be the mass of this block, which is 3 kilograms times 9.81, times the distance it changes, right, from here to there. So that's going to be one of those very common things where we take B and we're going to subtract out this B. This thing's length is also B, but we're going to subtract out B times the cosine of this angle. So we've seen stuff like that before, where we have mg, we'll say delta y 1, 2, right? So it's mg, and then it's going to be b times 1 minus the cosine of theta. And you should be able to work that out, why that is right there, okay? So the mass is 3 kilograms, 9.81, 1 minus the cosine of 60 degrees. I think that's just going to be 0.5. And can we fit him into there? I have the numbers in an Excel spreadsheet. Let's see. That potential energy ends up being 26.49. And these are metric, so they're Newton meters, joules. And the work between 1 and 2 is 0, right? There's no external work going on. And then the kinetic energy at state 2 is going to be 1/2, and maybe we should say this is mass of A right there. Yeah, there you go. And you're going to have the mass of A times the velocity of A at 2 squared. So 1/2 3 VA2 squared. So putting these in there, you could really just see that potential energy is going to turn into kinetic energy right here. So we'll put them back into the equation up here. We have 0 plus 26.49 plus 0 equals, I'll write it up, 1.5, right? I think we can do that in our head. 1.5, 3 divided by 2. VA2 squared plus 0. because this is at the, I forgot to write that PE2 is equal to 0. Sorry. I should have written that because it's at the datum. So yeah, we could write that the VA2 is going to be equal to 4.202 meters per second. So now we know what the speed of this little hammer thing is going to be. And now it's going to be between these 2 points. Now we have an impulse momentum problem going on between states and momentum. So yeah, let's write out a little bit of like what we were doing here. Here's the work energy. Now we're going to do the impulse momentum. Impulse momentum. Okay, and so we have like in a diagram the initial, the impulse, and then the final. So I'm just going to draw it locally. We don't have to draw up the whole big thing. Okay. So we have this guy moving right here. So he's going to be MA VA2 moving in that direction. We have equal and opposite impacts. And then we're going to have after the fact, we'll just assume these are in the positive direction. So we're going to have MA VA3 and MB VB3. This one's starting from rest right here. So let's write, I guess I'll write underneath this. Actually, I should make this 2 and 3, right? 2, and I'll turn that into a 3. I cheated. Okay. So writing this thing out, the mass is going to be 3 times my 4.202 plus 0, because these cancel out, is equal to 3 VA3 plus 1 VB3. So let's put those two things together, and we end up with 12.61 is equal to 3 VA3 plus VB3, and that's going to be my first equation. Now we're going to use the coefficient of restitution. We write out V A, I think I like B first, right? VB2 minus VA2. We could put the normal onto the thing, but it doesn't matter. I mean, the normal does going right through there, but we only have it one direction, so we're totally cool. And so we're going to get V A3 minus VB3. And so let's see, VB2 is 0. And this is our 4.202. And our coefficient of restitution is 0.7. And here's unknowns. So what we're left with, I believe, did I do anything wrong here? No, I think I'm okay. I'm going to have a negative 3 something. I'm losing track here. I think 2. 2.941. Is that correct? Let me see if I can move the keyboard out of the way. Yeah, I think that's correct. Focus. There you go. Focus here. Something to focus on. Okay. And VA3 minus VB3. So here's equation 2. Combine 1 and 2. All right, so let's see. I really care about B more than A, although I will need A at the very, very end of all of this. So I got to get both of them. So I'm going to solve this one in terms of A. So that comes up VB3 minus 2.941. Did that right? Yeah. And so put him back up into 1. So I get 12.61 is equal to 3 times VB3, 3 times 2.941 plus VB3. Now, hopefully, I will get VB3 correctly. Let me just double check with my handy dandy Hewlett Packard calculator here. And so I get 12.61, and I'm going to take 3 times 2.941, and they add together, and then I'm going to divide them by 4, and I get 5.35 change. So I know I did it right. 5.358 meters per second, which I can put back into this right here. So I subtract it out. I can subtract out 2.941 out of this, and I should come up with a 2.416 meters per second, and we can start a new page. What page is this? This is page 6. Boom. Okay, so now it's going to go. We're up to right here, and we want to get up to there, right? So now we want to try to figure out the y, right? So we're going to have like, here is going to be the datum, and then here is going to be the height of this thing. Okay, so let me do the work energy again. So this is problem 3, continued. Dot, dot, dot. And we're going to do work energy again. And take KE3 plus PE3 plus work done between 3 and 4 is going to be equal to KE4 plus PE4. So KE3, and this is only for particle B. Okay. Now I know that the other thing is still moving, but we don't care. They're not touching each other, so we just want to see how far B goes up. So it's 1/2 MB B3 squared. That's 1/2 1 kilogram 5.358 squared. So we find KE3 is 14.35 Newton meters, aka joules too. The potential energy at 3 is 0. We're going to treat that as the datum. The work done between states 3 and 4. Nothing external. Thank you. The KE at 4 is going to be equal to 0 because it's going to stop. And it's going to go up a height. And I'm going to go ahead and say MBG. And I'm just going to go delta Y from 3 to 4. So we know it's got 1 times 9.81 delta y 3, 4. Now the thing we actually want to get is that distance s, but let's deal with the geometry of that later. We're going to do it all in one step. So writing that back out, let's see, KE 14.35 plus 0 plus 0 equals 0 plus 9.81 delta y 3 to 4. So we get delta y 3 to 4 ends up being 1.463 meters. Okay, so now that is the distance it has elevated, right? But we need to first subtract out this distance right here, right? This one and there, right? So we got to kind of figure out what that is. I think it's easier to draw like a little triangle. So I'm going to draw like a little triangle. Because it's easier, I'm going to do it. I'm only going to do things that are easy from now on. So I remember this a boss one time saying, let's only do things that are easy from now on. Okay, sure. This is the same length up to there, right? So really what we're trying to do is we're trying to get this height right there. We know that this and this are the same lengths right here. So this is very similar to what we had to do in that other one, right? Oh, and by the way, this length is A plus B. Make sure we're clear in that. That's because it's we're talking about coming to this one right here, and we're using beta, but we're using A plus B for that, because that's like the radius of the thing up to the center. So this is A plus B, and this is A plus B, that length from there to there, and this length from here to here. We want to find that right there. I got to give this a name, this thing right there, and I don't know what did I call it over here? I didn't even call it anything. I just said just that thing. I don't know. We got any name? Let's call it delta y BC. See, because there's B and there's C. Why not? Delta y BC. Delta y BC is going to be equal to A plus B times 1 minus the cosine of beta. You can see that, right? Because this distance from here to here. By the way, I should have made that come up like something like that right there. I'm not being very neat. That's not very. Anyway, yeah. All right. So here's beta right there. So cosine, this times the cosine of beta is going to be this length, but we want this length, so we subtract that minus that. Oof. All right, so A was 0.6 and B was 1.6. And take 1 minus the cosine, and beta was 30 degrees. It's kind of boring. Come on back. Come on. Don't do that. And I think I get 0.3215. Is that true? Sure. 0.3125 meters. So if I want to get, let's call it, if I want to get S, it's going to be this distance. I'll call it delta y 3 to 4 minus delta y BC divided by, okay, and so here's a little also some information we're going to need, right? Okay, so right here, this slope is going to be beta, right? So you have to kind of either take my word for it or try it out for yourself to see, like, okay, that right there is perpendicular, and if I close this thing down, that closes down. Yeah, those have to be the same angle. So if we want to try to figure out this length, let's put it back over here. This length right here, we just figured out the height distance between here and here, right? That's what we have on the numerator right here at the top. So we want to divide by, we want the hypotenuse, so we're going to divide by the sine of beta. I know. So we're going to go 1.463 minus 0.3125. That'll give us this elevation change, and then divided by the sine of 30 degrees. And we get S is going to be equal to 2.283. Oh, come on. 83 meters. Yay! That was part A. Part B is to find the efficiency. Okay, so what is the efficiency? It's going to be the energy, the total energy before, right? Plus the, no, it's going to be the energy at the end divided by the energy at the beginning. And the energy at the beginning is going to be completely the potential energy. That's easy enough. But now we got to figure out what is the energy at the end. Well, that's going to be, we can do it a couple ways. One is going to be the potential energy at the end here, but you got to remember this thing is still moving. So what we could do is we could add that kinetic energy of this thing. We presume it's just swinging back and forth. We don't know. But at the end here, this thing has potential energy. So we have this potential energy, and we have this. We could also, if we wanted to, we could take this kinetic energy plus this kinetic energy, but after the impact, right? So what I need is the energy. So I'll write down the efficiency. It says what you want, and that's really what we got after we're done. What you paid for, right? So that's going to be the kinetic energy of A at 3, right? Plus the potential energy, because I already have it written down somewhere. Well, actually, I could do the kinetic energy at 3. There's no losses between 3 and 4, so let's go to the kinetic energy. Let's just say the kinetic energy at 3. There you go. The total kinetic energy at 3 divided by the potential energy at 1. So we are going to need more than just this kinetic energy, because this is only of part B, right? So we need kinetic energy of 3, let's say. It's going to be 1/2 MA VA3 squared plus 1/2 MB VB3 squared, right? So we actually already have this, but this one we didn't calculate yet. So we have 1/2 3, and remember we found a 3 here of 2.416. And we added, we could actually, don't need to write this whole thing out right here. We could just say we know that it is 14.35, because that's what we had up here, right? That's just the kinetic energy of B. And so what we find, I didn't actually calculate this, so let's calculate the thing out. All right, that goes out to 8.757. That's what that equals, and 14.35. Add them together. So we have 23.11 Newton meters. So the efficiency is going to be 23.11 divided by the potential energy at 1, which you recall was 26.49 from that first page. 26.49. let's see, 26.49. Divide that out, and I get, woohoo, the same thing, 87.23%. All right, so the answers for A, S is equal to 2.28 meters. B, eta is equal to 87.2%. That's a pretty good result, I think. Right? Somebody needs a haircut. That's what I'm thinking. Look at that. Oh, look at that. Beautiful, beautiful locks. Flowing locks. So, what do we got at the end for those who have come this far here? We have a traveler guitar. Do we have a guitar pick somewhere? I think we have a guitar pick somewhere. Are there any amplifiers? I don't think I have my little amplifier thing here. Yeah. Probably get in trouble. I have this little smoky amplifier. I wonder if the battery's dead. It sounds horrible. Let's see. It's close to being in tune, actually. It's almost in tune. Let's see if the little smoky amplifier is hanging out here. He's hiding in here. Where'd you go? Smoky? I don't know. I'm lost in here somewhere. Why are we having a conversation? Because you're really tired. Alright, let's see. We'll put you down there for now. Oh, you dropped your pick. It's on forever now. Oh, there it is. Where's the little smoky, though? You really don't know what I'm talking about. You think I'm losing my mind. I might be losing my mind. Very well might be losing my mind. But if I could find it, I'll show you what I'm talking about. Oh, there it is. And so they made these little amplifiers. They used to make them out of cigarette packs. That's really weird, isn't it? But I guess that people kind of like, I don't know, they got over that after a while. The novelty wore off. And now they just make them out of like plastic. It's half a watt. It looks like this right here. See that little thing? And what's really amazing about this is it can actually drive a guitar cabinet, a full-size 412 cabinet. One of these is the input. One of the okay, so this is the one of them is an extension speaker. So yes, I hear a little juice. All right, so let's see. Look, check that out. This is the tuning song. Sounds terrible. It sounds out of tune. Here, we'll tune it. So this is for those that really want to see the end. Yeah? There's a tuner in here somewhere. Yeah, it's not you. You're not a tuner. Where did you go, tuner? There you go. It's my little tuner. See how far off you are. It's not bad. That's terrible. that could also. I don't think it's gonna sound, but anyway, this thing, this is my Traveler guitar. You can see how small it is. It's got the little tuners, or really kind of cool. It's like a partnership with LTD, which is part of the ESP family right there. It's got a built-in distortion that kind of sounds like badass.